Hi everyone, this is CS188, Exam Prep Section 4. So, the first question is about just MDP Basics. So let's take a look at this MDP. So, in this MDP, the reward is given along these edges. So this has a reward of 10, these have rewards of 0. And transitions are all deterministic. So if you make a transition, you will succeed with probability 1. Okay, so for this question, for part A, let's assume that the max horizon length is 15. That means that you are able to look 15 steps ahead. And it says that this discount factor is 1. So that means that reward 15 steps away will look exactly the same as a reward 1 step away. If we're at option A, well, the optimal action, there's only one action you can make because you can't go back to B. So the optimal action at A is to go to A. At B, now you have a choice. So at B, with 15 steps to go, I can come here to A, take the 10, and then at A, I have nowhere else to go, so just cycle around in 0. So if I choose to go this way in B, my reward will be 10. If I choose to go this way, then I have 15 steps. So I'll waste 1, 2, 3, 4 steps, getting no reward, coming over to F. But then I have 11 steps left to do this and just go around F and get 1s. So I'm going to take 1, 2, 3, 4 steps doing nothing, and then 11 steps here, gaining 1 every time. And so this gives me a total of 11 if I go right. So for B, my optimal action should be to go to C and get closer in here and come to F and cycle around 11 times. So using a similar argument for C, I'm going to come 1, 2, 3, and then cycle here 12 times, which is better than the 10. So C will take me to D. D will take me to E for the exact same reason, and E will take me to F for the exact same reason. And obviously, if you're in F, you'll want to stay there and cycle around 15 times instead of going back there and getting the 10. The second part of this question asks what happens if the horizon is infinite, and if it is infinite, does your selection of the discount rate affect what path you choose? So let's say that you're at D. There's only really two things you can do, right? Either I come over here, I get the 10, and then once I get here, I'm stuck in the A forever, so I'll get no more reward. Or I can come over here to F, and then I'll get the reward of 1 consistently. But it'll be discounted every time I get it because it's further and further away. So the question is, what are these two costs and how do they compare? So let's break it down. So the first cost is if I go over here and I grab the 8. So let's say I'm starting at D one more time. So this first step is not discounted. This gets 1 discount and this gets 2 discounts. So this reward of 10 will be discounted twice. And then if I'm here and I come here once, that's no discount. And then here's 1 discount. And then this step is going to give me a second discount. So this is going to start at the discount rate squared, and that's a reward of 1. And then the next time step, I'm going to cycle around in F one more time. That's going to give me a discount rate of, that's going to give me 3 discount rates, and the next time is 4 discount rates, and so on. And this goes forever because the horizon is infinite. So if you remember your rules for geometric series, this comes out to 1 minus, I believe, gamma squared over 1 minus gamma. And that's just a rule of geometric series. So if this one is greater than this one, then I'm going to choose to go here and grab the 10 reward and then hang around at A forever. If this one is greater, then I'm going to choose to come over here to F and cycle around in F forever. So the question is, does the discount rate cause this to change? Well, all you have to do is set them equal to each other and see if there's a point where they cross. So if there's a point where these two are equal, and after that point, this one is greater, and before that point, this one is greater, or vice versa, then you'll know that that's the point when this value changes. So the only thing left to do once you have that is to just apply it to all of these nodes. So it doesn't really apply to node A because node A, you're stuck there forever. So for the rest of these, the only question is, what's the discount rate that makes it worthwhile? Well, all we have to do is generalize, where did this 2 come from? Well, this 2 came from the fact that I was 2 steps away from B and then 1 more step to collect the reward, right? So instead of having this to be squared, let's just generalize this thing to be, let's say it's n, where n is the distance to B. So n is distance to B. So for example, if you're already at B, then the distance is 0, and so this 10 is not discounted at all, which makes sense. And then on this side, instead of this square, well, this square comes from the number of steps to F, because once I get to F, I can start just collecting all my discounted rewards. So this one should just be M, where M is the distance to F. Okay, sorry about the sloppy handwriting. And so this gives me this equation, and this equation will hold true for all the nodes B, C, D, E, and F. And so this will let me determine if the discount rate affects the value, or affects which path I go down. Question 2 uses the grid world environment that we're all familiar with. So in this example of grid world, there are no living rewards. The discount is just 1, so there's no discounting at all. And once you get to one of the terminal states, you need to exit the grid. So you need to use the exit action that results in the listed reward. Okay, so now let's think about what's the optimal value at A. Well, so if you're at A, well, the optimal thing you want to do right now, if the discount is 1, that means that there is no discounting. So the reward 10 is going to be still 10, no matter how many steps later I get it. So obviously I'm going to try to go for the 10. So I'm going to come here, 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 and then I'm going to exit, and I'm going to get the 10. So the optimal value ultimately is just 10. For part B, we're trying to run value iteration. It might help to pull up the equation to remember what it looks like, but there's actually a solution to this that's pretty conceptual, as long as you understand what value iteration is doing. So remember that value iteration is considering all of the reachable states from a current state. So in this case, this is reachable and this is reachable. And once you look at those states, consider the expected sum of rewards if I go to the state and I start acting optimally. And so v sub 0 sub s, v sub 0 of s is saying that given 0 steps to go, what's the optimal thing to do, and what's the expected sum of rewards if I make 0 steps optimally? Well, there's no steps to make, so everybody just has a reward of 0. Now let's try the first iteration. So in the first iteration, we're saying that you have 1 step to go. If you make that step optimally, what is the expected sum of rewards if you make it optimally? Well, if you're at the plus 10, your optimal move is to leave, right? Make the exit option, and that'll give you a reward of plus 10. And because there's no discounting, we can just say it's plus 10. Similarly, if you're in this step, your optimal choice is to leave. And so if you use the exit option, you'll get a reward of plus 1. So the values for v sub 1 are as follows. And there's nothing else you can do in these 3 middle states that allow you to get any reward. So those are still 0. Now let's think about v2. So v sub 2 is given 2 steps, what are the optimal? Given 2 steps and you act optimally, what's the expected sum of rewards you get given that you're acting optimally? So if you're an A, your optimal move given 2 steps is to come here and collect this reward 1, right? So that means that given 2 steps, you're going to come here, and then once you're here, you're going to act optimally according to v sub 1. Well, v sub 1 said that I exit and collect 1. So v sub 2 just says I come here and then do the thing that corresponds to v sub 1. And so if I do the thing that corresponds to v sub 1, I get 1, and there is no discounting, so this is now 1. And so that means that in the second iteration, vk sub a is now going to be non-zero, and it's going to take on the value of 1. And now you just kind of keep going with this. So you say, okay, well, in the third iteration, in the third iteration, I'm going to allow myself 3 steps. And so given 3 steps, if I act optimally in all 3 steps, what's the optimal reward I can get? So if you're in this state, well, now I can come here, and then v sub 2 tells me that in 2 steps, I can get a reward of 1. So I'm going to have 1 here, because in 3 steps, I can come here and then do the optimal thing here and get a reward of 1. Now the question is, how many of these iterations does it take until you find a v sub k of a that matches the optimal? Well, the optimal is 10, right? So how many steps does it even take to get this reward of 10? Well, we said that it takes 1 step, 2 steps, 3 steps, and then exit. So really, you'll never see that a is 10 until the 4th iteration, because the 4th iteration allows us to act optimally 4 times. And if you act optimally 4 times, you will get the reward of 10. So you have 4 iterations required to get that reward of plus 10. Okay, so I've redrawn the grid here just so we all remember what it looks like. So now we're going to assume that the discount rate is 0.5. So that means that at every step you make, the rewards get decreased by a factor of 0.5. So if that's the case, what's the optimal value? Well, there's only 2 things you can do, right? So I can come here and then grab the 1. So that's going to give me so it's going to give me 0 to get here with no discount. And then I'm going to get the 1, and that 1 is going to be discounted just once. The alternative is I can come right and try to get the 10. So if I do that, I'm going to move once, get 0. I'm going to move, so that's going to give me a reward of 0. I'm going to move one more time. That's going to give me a reward of 0 discounted once. I'm going to move one more time. That's going to give me a 0 discounted twice. And then I'm going to get the, it's twice. And then now once I'm here, I'm going to exit. So it's going to give me a reward of 10. That's going to be discounted 3 times. So this one evaluates to 0.5. And then this one evaluates to 10 over 8, which is clearly greater than 1, so it's greater than 0.5 as well. So that means that the optimal value is going to be 10 over 8. So part F just asks us to generalize what we came up with in part E. So now we're just saying that the discount factor can be arbitrary. So if the discount factor is arbitrary, well, all we have to do is just replace the 0.5 with anything arbitrary. So in this case, this was a 1 times the discount factor, so that's just gamma. And then in this case, well, I had the 10, and I had to discount it 3 times. So the question is just, if I want it to be optimal to go right, then I want this one to be greater than this one. So the equation I want to deal with is this is greater than or equal to gamma. And if you do a little bit of math and solve this, you'll see that this evaluates to gamma is greater than or equal to the square root of 1 over 10. And that is the requirement for us to choose this value over this value. Okay, so this question has a lot going on, so let's just make sure we know what everything is. So we have n cities that are arranged in a circle, and at every step, the poet can choose to go east or west or stay. So if the poet chooses to stay, then with probability 1, he's going to obtain a reward of r sub I. If the poet chooses to go east, then with probability of 1 minus p sub I, he's going to fail. And if he fails, then he gets a reward of r sub I over 2. And he's going to stay in location I. And if you stay, you obviously stay in city I as well. If you go east and you succeed, well, the probability is p sub I because you either fail or succeed. If you succeed, it says that the reward is 0. But you are now in state or city I sub plus 1 because you went east. If you went west, you get a similar distribution. So if you go west, with probability 1 minus p sub I, you're going to get the reward r sub I over 2, and you stay in city I. With probability p sub I, you're going to get a reward of 0 for successfully traveling, but you're now in city I minus 1. So for part A, we're going to assume that r sub I is equal to 1, p sub I is equal to 0.5, and the discount factor is 0.5 for all I. So the first policy they want us to evaluate is v stay of I. This means that you're going to be staying in the same place over and over. So if you do that, you're going to be following this distribution, which means that you'll always get the r sub I with certain probability, like 1 certain probability, and you'll always be staying in I. You'll never go anywhere else. So this means that in the first step, you'll collect r sub I, and then the second step, you'll collect r sub I with a discount factor. The next step, you'll collect r sub I with 2 discount factors, and so on until infinity. And if you plug in the values, this gives me a 1 and a 0.5 and a 0.5 squared. And if you evaluate this as an infinite geometric series, I have a1 over 1 minus r, and that gives me a total value of 2. Next, we want to evaluate the policy v west of I. So this is saying that always go west. So remember that to evaluate a policy, what we do is we're going to sum up across all possible places this policy will land us. And at every one, you want the transition probability of starting in your current state, taking the action that's provided. So pi sub s is the option that's provided by the policy that we're trying to evaluate. We're going to land in S prime. So the probability of this happening. And then once I have this, I need the expected discounted sum of rewards. So what's the reward of doing that? Plus take a discount factor of once you're there, how do you keep acting according to that policy? So this is what we want to evaluate. So let's consider the 2 things that can happen, because if you always choose to go west, then the 2 s primes you're allowed to land in are, well, you can land in I or I minus 1. So you land in I with probability 1 minus p sub I. So this is now just going to be plugging in numbers. The reward, if I land in 1 minus p sub I, is r sub I over 2, plus if I have a discount factor. And notice that this, once you land in the state of I, looks exactly the same as your current one, right? So v west of I is equal to, well, this is exactly the same, v west of I, because you're in the same state. And then with probability p sub I, you're going to get a reward of 0. And then, again, you need a discount factor, but you're in state I minus 1. But recall that for this part of the question, R sub I, P sub I are the same for all I. So it doesn't really matter what city you're in. Every city pretty much looks exactly the same. So this is technically supposed to be V sub west of I minus 1, but we know that every city looks the same, so this is really just V west of I. And now notice that this is a linear equation, right? So you can substitute the P sub i's with 0.5s. So this is just a 0.5, right? This R sub I, as we said, for all cities is 1. This P sub I is a 0.5. And so now notice that, and the learning factor, the learning rate is also 0.5. And the learning rate here is 0.5. So notice that the only unknown in this equation is the V west of I, and everything else is known. So if you just go ahead and solve this out, you'll get that V west of I is equal to 1. Now in part B, we have that P sub I is equal to 1. So this means that if the traveler chooses to travel, he's going to succeed with probability 1, but he's going to collect that reward with 0 with probability 1 as well. And then now we're going to say that for all even cities, there's a higher reward A, and for all odd cities, there's a lower reward B. So if you start an even number city, then you're going to be collecting the higher reward. So are there any values for the discount factor that will convince you to not stay at your current city? Well, thinking about it intuitively, if I choose not to stay at my current city, that's saying that I'm going to take the cost of 0 to move and travel instead of staying there and collecting the higher reward A. And also now I'm in a new city, and that new city has a reward of B, which is even lower. So there's pretty much intuitively, there's really no reason that you would ever leave your current city. And so just thinking intuitively, this answer should just be all values of gamma. So part 2 is a little bit weirder. So part 2 is now saying I'm starting in the odd city. So the city I'm in has the lower reward right now, and it's asking, is it ever worth it for me to go to the higher reward versus just staying in the one with the lower reward forever? So for this one, we need to actually do a little bit of computation. So if I stay in the odd city forever, well, the odd city, if I stay there and just keep staying there, if I stay there once, it's the reward of B. If I stay there twice, then it's B with a discount factor, and the next time with B with 2 discount factors, and so on. If I choose to move to A, then first I have to travel, right? And that traveling step is going to give me a reward of 0. But then once I'm there, I'm going to get the higher reward A discounted once, plus the higher reward A discounted twice, and so on. And so the question is, when do I ever prefer to stay at the current city? Well, staying at the current city is this one. If I want to prefer it, then I need it to be greater. And so if you remember your geometric series, this one comes out to B over B minus lambda. This one, if I let this be A, then it's A over A minus lambda, but it's actually 0, not A. So you have to subtract out the A, and you keep the inequality. And if you do a little bit of algebra and solve this out, you'll notice that this is true if gamma is greater than B over A. And finally, it says that if we start at an odd number city and gamma does not lie in the range, well, then what happens? What's the optimal policy? Well, if gamma does not lie in this range, then we have that this is true. And so that means that you're going to be choosing this one instead. And so how do we describe this policy? Well, we said that you're going to travel to the even one and then stay in the even one forever. For this part of the question, we're assuming that the optimal value of being in city 1 is positive. So that means that given that you're in city 1, there is some set of optimal moves you can make that will give you some positive reward. Okay, so now it says that n is even. So let's just come up with an even circle of cities. So if n is equal to 4, it would look something like this. So notice that all the R sub i's are greater than 0. So the rewards for staying in the city is at least 0. But there's no way that they can all be 0, because if they're all 0, then there's no reward to be gained. So traveling and staying will give you no reward. But it says that there is some optimal move you can make from one that will give you a reward. So that means that one of these has to at least have a reward of greater than 0. So let's just say this is node I. So let's just say that this is node I, and that this node has some sort of reward that's strictly greater than 0. Well, if that's true, then when we run value iteration, remember that the 0th iteration of value iteration says that with no moves left, what's the best thing I can do? Well, the best thing I can do is just, well, there's no moves left. I can do nothing, so they give me a reward of 0. But if I'm in city I and I have 1 move left, so this is the first iteration of value iteration, then given that I have 1 move left, well, I can stay there and collect the reward R sub I. So this is going to be, R sub I, which, as we note, is greater than 0. And V2 of I will similarly be, well, I'm going to stay in that city, collect R sub I. I can also stay there again, and I can collect another R sub I possibly discount it. But note that the discount factor is positive, so this whole thing will still come out to be greater than 0. Now let's think about what happens in the second iteration for some other cities. So let's have a city I minus 1 here. So given that you have 2 steps left here, well, something you can try is to come here and then collect this reward, right? And even if that doesn't happen 100% of the time, well, somewhere in that summation, you're going to have something that looks like, well, with probability p sub I, I succeed in moving here. And then once I'm here, I can collect the reward of 0 because traveling gives me a reward of 0. But then with a discount factor, I'm going to act optimally here with 1 step left. So that's v sub 1 of I. But note that this term is positive because it's a probability. This term is positive because it's a discount factor. And this term is also positive because we noted that this term is positive right here. So that means that overall, this thing is also going to give me a strictly positive number. And for the same reasoning, I plus 1 here is also going to be positive. So again, somewhere in your list of potential actions, one of the actions is going to be to move here. Or sorry, the optimal action is always going to be to move here. And with some probability, you are going to succeed. And then if you succeed, you can come here and act optimally with the v sub 1 of I, and that's going to be greater than 0. So note that in general, what's happening here is that we said that this city I has some probability greater than 0. And in the first time step, that allowed this thing to be greater than 0. In the second time step, that also allowed these two to be greater than 0. So in general, you're basically spreading this value here across. Because given the more time steps, the further away you are, you can actually come over to the city and obtain the reward here. And so as the number of iterations goes up, you're going to start spreading out. And so that means that in the third iteration, this one will also have a non-zero value because given 3 steps, I can come here, I can 1, 2 steps, and then stay here, and that'll give me some sort of reward. And even if it doesn't happen with 100% probability, because of the fact that at least one of the terms in your summation accounts for the fact that it's successful, you will have some non-zero value. So now let's think about what's the worst case, because it asks us for the largest case, the most number of iterations, that this thing, that one of those cities, city 1, stays 0. So the worst case is that your city 1 is really far away from the city that has a reward. So let's say that this is the city with a reward, and let's say that this is city 1. So it's the furthest away it can be. So it can be right across the circle. So that means that in iteration 0, all of them are 0. In iteration 1, this one is hit. Iteration 2, these two are hit. And iteration 3, this one is hit. So in general, the formula you're going to see is that to go halfway around the circle, you have to account for n over 2 nodes. You have to go n over 2 nodes to cross halfway around the circle. And then because of that fact that this one started at iteration 1, you have to add 1. And another way to see that is just to note that in this case, the n over 2 was equal to 2 because there's 4 nodes, but the actual number of iterations was 3 because you had 1, 2, 3. So the final answer for this part is n over 2 plus 1. For this last part, they give us for this last part, we get a map of 3 cities. So city 1, city 2, and city 3. In city 1, the reward for staying in city 1 is 0. The reward for staying in city 2 is 2. And the reward for staying in city 3 is 3. And the probability of successfully traveling between any of these is 0.5. The discount rate is also 0.5. So if you're in city 3, what's the optimal policy there? Well, the optimal policy is probably just to stay there forever, because if you're in 3, this is already the highest reward for any of the cities, so there's no reason to go anywhere else. So that means that the optimal value associated with that policy is just going to be collect the 3 for staying there, and then remember that staying there is deterministic. You'll always succeed in staying there. So with the discount factor of 0.5, I'm going to get another 3 by staying there. With the discount factor of 0.5 squared, I'm going to get another 3, and so on. And as a geometric series, this is 3 over 1 minus 0.5, and that comes out to 6. The next one asks about the optimal policy if you're in 1. Well, if you're in 1, you're currently getting no reward, so this is probably not the best policy to stay here. And in fact, your best policy is probably to come here to the best state and try to stay here forever. So remember that the formula for doing value iteration comes out to try all the possible places you can land. Think about the probability that you land in that spot, and then once you're there, think about the reward that you get for landing there, plus the discounted best thing you can do if you stay there. So if we try to just plug this in for here, so we're going to have a v star of 1 is going to be equal to, well, with 0.5 probability, I succeed. So with 0.5 probability, the S prime is going to be 3 because I succeeded. That's going to give me a reward of 0 because traveling gives me no reward. But I am now in S3. So with a discount factor of 0.5, I now have v star of 3. And in the previous question, we also know that this is 6. The other possibility in this summation is that with 0.5 probability, I fail. If I fail, I stay in R1, which still has no reward. And again, I try to discount. And if I discount, I'm still in R1, so I just have to figure out what the optimal value of R1 is. So we know that the optimal value of staying in state 3 is 6. And we know that now all of this is filled out, except for v star of 1. So this is just an equation with one unknown. And so if you solve this out, you will get that v star of 1 should be equal to 2. Finally, now they want the q value of being in 1 and staying. So remember that a q value is the same as the optimal v value, except that the q value is giving you an action to do. So now you're in city 1 and you choose to stay, even though that's not optimal. But what if you choose to stay and then act optimally afterwards? So the only difference between the q value and the v value is that you're given the action. So again, the equation remains the same. If you choose to stay, well, staying happens with probability 1. And then I'm going to collect the reward for staying, which is nothing. And then with the discount factor of 0.5, I'm going to try to do the best thing I can at state 1. Well, the best thing I can do in state 1, as we calculated before, the best value I can get there is 2. So this is just going to give me a 0.5 times 2, and that is 1. And with that, we should be done with this entire worksheet.